Assalamu alaikum and hello everyone. Today I'd like to discuss one of our courses titled ANI 503, that is Applied Animal Breeding. This work is dedicated to my friends, classmates and special people. Okay, now to begin. Remember that it was said that this course is a prerequisite of the previous UG3 ANI 303, that is Animal Breeding and Genetics. The course started by outlining genetic parameters, which I think are those measurable stuffs about genetics, predictable ones inclusive. It starts with heritability. Well, before I go to that, I will outline some few things to build our foundation for understanding it. Okay, heritability estimation is primarily carried out on metric traits, aka quantitative traits. Okay, what are metric traits? Well, metric traits or quantitative traits, whatever you'd like to call it, are those traits that are measurable and can be expressed numerically. That is, they are traits you can measure and write them in numbers format. For example, milk yield, which can be measured in liters, 1 liters, 2 liters, etc. Height in centimeters or meters. Weight in kg or grams. Length as well, and liter size, etc. Unlike non-metric traits, aka qualitative traits, controlled by one or a few number of genes, quantitative traits, i.e. metric traits, are governed by many genes. Okay, remember a statement from ANI 303. The basis for quantitative genetics are based on the idea that these traits are governed by many genes. Good. That being said, quantitative traits are the ones that are more often of interest to farmers and breeders. Now, phenotype. What is phenotype? It is the term used to describe what you see physically about an organism, including qualitative traits and quantitative traits. Qualitative traits such as eye color, presence of horns, and also etc. Yeah. Genotype is used to refer to the inherent makeup about an organism or genetic makeup. Now let's discuss variance. What is variance? Just take variance as simply the difference or variations in something. Phenotypic variance, merging the two terms, phenotype and variance. Remember, phenotype is what you see. Variance is the difference. So it means the difference or variations in what you see in organisms. In this context, it's simply just the statistical variance of phenotypic traits. You do remember what variance is, right? Okay, I will take back a bit. Yeah. Remember, statistic is of two types, descriptive and inferential. Descriptive is used to summarize and describe data, while inferential consists of making decisions, inferences about a population based on sample data. It often utilizes probability theories. Okay, descriptive statistics include the measure of central tendency, which are the mean, median, and mode. Dispersion, which include variance, standard deviation, coefficient of variation, etc. Visual representation, including pie charts, bar chart, box plots, etc. Okay, our main interest is the variance, which measures on average how far data points differ from the mean. Is defined more formally as the average squared deviation of individual data points from the mean. In Hausa, yayin da suka bambanta juna, yayin da lambobi suka bambanta da juna. Okay, the symbol for variance is sigma square. Just know that whenever you see that symbol with the square on top, it represents variance. So, phenotypic variance is sigma square p. Genotypic variance is sigma square g. If you remove the square from the sigma, that is the standard deviation. Remember, phenotype, as always emphasized by our teachers, that it is the combination of two entities, genotype and environment. So P equals G plus A. So the variance representation is also the same. Sigma square P equals sigma square G plus sigma square A. But genotype can also be partitioned based on gene interactions. Genotype equals A plus D plus I. That is additive plus dominance plus epistatic. Additive genotype is the one that consists of additive effects of genes. Suppose for a specific trait, let's take height for example. You know that this is a quantitative trait, right? Which is also measurable, which we say that it is governed by many genes. So supposing each individual gene potentially contributes 2 centimeters to an animal's height. If we have 50 genes controlling height of animal, then 2 centimeters plus 2 centimeters plus 2 centimeters up to 50 times, making 100, will lead to the expression of an animal's height to be 100 centimeters. That is additive effect, and it is the one we are interested in, which is transferred predictably to the offsprings. The dominance, we all know what it is. It is as a result of interaction of genes at the same locus, where one gene overshadows another. It can be expressed, it's often expressed in letters. For example, let's say capital letter A and small letter a. The capital letter represents the dominant gene, while the small letter represents the recessive gene. The epistatic. The epistatic is coined from the term epistasis. Well, I need not to define that. However, epistatic happens with interaction of gene at multiple locus, that is loci. So expressing it in variance term, you have sigma square G equals to sigma square A plus sigma square D plus sigma square I, meaning the genetic variance equals the additive variance plus dominance variance plus epistatic variance. Okay, recall we said from the formula sigma square P equals sigma square G plus sigma square A. Heritability is the proportion of the phenotypic variance that is due to genetic variance. I hope so you understand what this means. Anyway, let me give a useful analogy. Take for instance, in a class 20 students are male and 30 students are female. So what will be the proportion of the males in the whole class? Okay, the whole class are 50 students, yeah, right? That is if you sum 20 and 30, making 50. So the proportion of males are 20 all over 50, same as 2 all over 5, which is equal to 0.4. The proportion of female is 30 all over 50, which is equal to 3 all over 5, which is 0.6. Okay, let's end this bizarre yet useful analogy. Similarly, from the formula, sigma square P equals sigma square G plus sigma square E. So proportion of phenotypic variance, sigma square P, that is due to genetic variance, is same as saying the proportion of genetic variance in phenotypic variance. It is expressed mathematically as this: H square equals to sigma square G all over sigma square P. That is the symbol. H square is the symbol for heritability. Okay, the environmental part that I haven't forgotten about. We know that heritability in essence is the percentage of genetic variance in phenotypic variance versus environmental factors. Remember that environment also contributes to the phenotypic variance, just like males contribute to the population of the class in our previous analogy. Good. Simply put, heritability measures how heritable a character is. Is it due to genes or environment? Okay, heritability is defined in broad and narrow senses. In a broad sense, it is the proportion of phenotypic variance that is due to overall genetic variance. Additive, Dominance and epistatic. Inclusive. Yeah. Mathematically, it's expressed as HB square. That is the broad sense heritability equals sigma square G divided by sigma square P. Conversely, in narrow sense, it is a proportion of the phenotypic variance, that is additive variance. It is probably what we are more interested in quantitative traits. After all, they are governed by many genes, particularly additive genes. Mathematically, it's expressed as Hn square or sigma square A plus sigma square P. It is said that theoretically, H square ranges from 0 to 1. It is said that theoretically, H square ranges from 0 to 1, but the extreme values are rare. From the table in our notes, showing average heritability estimate of some economic traits, let's look at some and discuss. Heritability closer to 0, for example 7% or 0.07, means a trait is very lowly heritable and it is not advisable to use in breeding, even if the animal produces well. The observed effects we see may be just due to environmental noises. Heritability about 36%, that is 0.36, means the trait is moderately heritable. Those with 60% or 0.6 are very much heritable. A selection of the animal by phenotype is justifiable. Now let's go to estimation of heritability. It is said to measure heritability, a large amount of data is required. Yeah, there are two common methods used in estimation of heritability. One is the parent-offspring relationship. Two is the paternal-half-sib relationship. Remember that it is said that the underlying principle in heritability estimation is resemblance among relatives. Well, I need not to explain that. Okay, in parent-offspring relationship, values for offspring are regressed on those of the either of the parents. Let's just jump to the calculation. It means the offspring values are taken as dependent variable since it is the one being regressed. Suppose you want to estimate the heritability of weaning weight. You can take the measurement of both a dam and an offspring in the same environment. You can take the weaning weight of dam and offspring as x and y. Now, this is getting too tough. Okay, to simplify this, I will just write the formula for H square. Heritability H square equals 2 times BOP. The slope BOP is calculated by the formula BOP equals summation of xy minus summation of x times summation of y all over n, all over summation of x squared minus summation of x all squared all over n. I don't want the explanation to get complicated. However, the 2 as a result of the two there in the equation for heritability is as a result of the random half gene contribution from parents. For example, the table of sire progeny values for weaning weight that has been collected, it says that heritability should be calculated. Okay, our independent variable is I think that of the sire value, which we will denote as x, and progeny, which we will denote as y, which is the dependent variable. H square, okay, to calculate this, H square equals 2 times BOP. We'll have to first determine the value for BOP, that is the slope. BOP equals summation of xy minus summation of x times summation of y all over n, all over summation of x squared minus summation of x squared x all squared all over n. Using the table, we'll calculate each component. First, let's calculate the summation of xy. First of all, we'll determine the value for xy for each column. We'll multiply each sire value by its corresponding progeny value. Let's start with 3 times 6 equals 18. 4.3 times 6.7 is 28.81 up to the end. The next component is the summation of x. We'll sum the value for the sire, which is 3 plus 4.3 plus 4.8 up to the end, which gives us 68.6. The summation of y, which is the summation of the progeny value, equals to 6 plus 6.7 plus 6.8 up to the end. Our n is the sample variance. Our n is the sample size, which is equals to 12. The denominator, which is equals to includes a component summation of x squared, the crude sum of squares. To calculate the crude sum of square, from the table we will take square of each sire value, that is x squared. 3 square equals to 9, 4.3 square equals to 18.49, 4.8 square equals to 23.04 up to the end. Summation of x all squared. To calculate that, we'll square the summation of the values for sire, which is 68.6 squared. N is also the sample size. Okay, now to substitute the values. Okay, if we sum the value for xy, it will give us 497.48. Summation of x, which is 68.6, summation of y, which is 86.2. Summation of x squared, which is equals to 412.56. Summation of x all squared, which is equals to 4705.96. N is the sample size. So the correction factor from the denominator, summation of x squared all over n, equals to 4705.96 divided by 12, which will give us 392.163. Now let's substitute the values. BOP equals to 497.48, which is summation of xy, minus 68.6 times 86.2 divided by 12, all over 412.56 minus 392.163. BOP equals to 497.48 minus 492.77 divided by 20.397. BOP is equals to 4.71 divided by 20.397, which is equals to 0.231. Now to calculate h square, which is 2 times BOP, which is equals to 2 times 0.231, which is equals to 0.462, which is equals to 46.2 if expressed in percentage. This means that 46.2% of the phenotypic variance is due to genetic variance. The next one is the paternal half-sib relationship, which is often preferred to avoid maternal effects. I wanted to ask about the principle behind this and why we do use ANOVA. But let's just stick to understanding the ANOVA table. The ANOVA table includes different components, including the source of variation, degree of freedom, sum of squared, and mean square, and also the expected mean squares. Remember, in ANOVA, it compares the between group sum of squares to within group sum of squares. Similarly here in estimation of heritability, it's the same. So between group sum of square among sire, that is between sires. From the table, the degree of freedom for between sires is s minus 1. For within sires, that is the error, is s into bracket of n minus 1. The degree of freedom for total equals to sn minus 1. Once the sum of squares are determined, the mean square can easily be determined by dividing the sum of square by the degrees of freedom. Later on, the mean square are equated to some symbols in expected mean square. For instance, the total mean square is equated to sigma square p, that is the phenotypic variance. The error mean square is always equated to sigma square e, the error variance, while the mean square between sires is often equated to sigma square e error variance plus n times sigma square s sire variance, that is. For example, a table consisting of some source of variation, sum of square, degrees of freedom, mean square, and error, mean square of values. It also has the component between or among sires, within, error, and total. Between sire sum of square is 0.433, within sire sum of square is 2.598, and the total is 3.031. Degrees of freedom between sire or among sire is 7, for within sire is 112, for total is 119. So to determine the mean square, we will divide the sum of squared by the degrees of freedom. For between or among sires, 0.433 divided by 7 will give us 0.062 for mean square between sires. For within sires, to determine the mean square, we'll divide the sum of square for within sires, that is error, divided by its degree of freedom. 2.598 divided by 112, which is equal to 0.023. For total, is 3.031 divided by 119, which is 0.025. Now to determine the expected mean square. The expected mean square is equated. The mean square is equated to these symbols. For the total, the value for mean square for total is equated to the phenotypic variance. The value for mean square for error within sires is equated to the error variance, sigma square E, while the mean square for between sires is equated to error variance plus n times the sire variance. The expected mean square for between sires is then equated to the mean square. Now, often using this value, we will be told to calculate the heritability. Heritability for paternal half-sib relationship is expressed as 4 times sigma square S all over sigma square P. That is 4 times the sire variance divided by phenotypic variance. Remember from table, the mean square between sire is equal to 0.062, which is equated to the error variance plus n times the sire variance. So the error variance is 0.023. So if we try to substitute the value, therefore 0.062 equals to the error variance plus n times the sire variance. Okay, let's not make this complicated. Let's simplify the formula by making the sire variance the subject. If we make the sire variance the subject, we will get the equation. The sire variance equals to mean square sire minus the mean square error divided by n. N represents the number of terms. Here in our question is equals to 5. Okay, let's summarize this. To estimate the heritability for paternal half-sib, we will need to understand two main equations. We'll take down two equations, h square and the sire variance. H square heritability. H square equals to 4 times the sire variance divided by phenotypic variance. The sire variance equals to mean square sire minus mean square error. Mean square sire minus the mean square error, which is the error variance divided by n. From the h square formula, from the table, sigma square p phenotypic variance equals to 0.025. Mean square for sire from the table is 0.062. The error variance from the table is 0.023. If we substitute the value in calculating the sire variance sigma square s equals to 0.062 minus 0.023 divided by 5, which equals to 0.039 divided by 5 equals 0.0078. Therefore, h square equals to 4 times 0.0078 divided by 0.025 equals 4 times 0.312. H square is equals to 1.248. Although this is not intuitive because H square from the note says it ranges from 0 to 1. But this is just theoretical. Thank you so much for listening. I pray say we pass this course.